December 2015, the world will meet in Paris for yet another climate summit. So far, Warsaw failed, Durban failed, Copenhagen failed. The French government has declared that they are not going to fail. So the question is, how are all of us going to do this? Europe is attempting to lead the way on reducing CO2 emissions, and the rest of the world is not following. This is for sure. The Chinese, the Indians, the Russians, the Canadians. I'm Canadian, so I can say that. I have to credit the Canadians because at least they were honest. They said, no, we're not going to do it. That's it. Okay? So not all of them have said, we're not going to do this, and Europe can do what it wants, but we're not going to do it. So how are the Europeans going to convince the rest of the world to meet their 40% reduction targets, which is what they're going to aim for in Paris? Well, what about using greenhouse gas emissions as products, as materials? We have been so convinced by the environmental movement, and I can say this because I come from the environmental movement, I come from Greenpeace. I was on the board of directors of Greenpeace in the 1980s. The environmental movement has convinced us that CO2 is really a bad thing. And so we all think, okay, CO2 is a bad thing, we have to get rid of it. But actually, we wouldn't be here without CO2 because our plants need it to survive. CO2 is a valuable and rare chemical. There's only a very tiny amount of it in our atmosphere. And in fact, human technologies are the only technologies that concentrate CO2 to the extent that we can use them as products. Because we're not smart enough yet, like plants are, to actually suck these tiny amounts of CO2 out of the air and reuse them as products. We have to actually concentrate the chemical ourselves so that we can actually suck it out of the smokestacks and then use it for industrial purposes. And what I'm about to show you now are some examples of how greenhouse gas emissions are being used for products and for industrial purposes. So this is the question that we face for Paris 2015, but not just for Paris 2015. Twente University, the city of Venlo, the Netherlands have this challenge, and they have this opportunity staring at them right now. So the question is, that's the question. Right now, we look at it as the second problem, but not the first opportunity. So, I would just like to explain to you something called supercritical CO2. How many people have heard of supercritical CO2? 1, 2, 3, okay, so let's say 10% of you. Supercritical CO2 is, I'm sorry for the French, but we first explained this in Paris and I haven't had a chance to translate it yet. So this vector is pressure and this vector is temperature. So at a pressure of about 72 bars and a temperature of 31 degrees Celsius, which is, just a warm day, basically, CO2 takes on a unique characteristic that is halfway between a gas and a fluid. And that's called supercritical, because it reaches a critical phase. And something happens to CO2 when it becomes supercritical. It becomes a wonderful solvent and a wonderful lubricant. A fantastic product. And because of that, it is being used now to replace toxic solvents in all kinds of cleaning processes, for example. So there are literally hundreds of use for supercritical CO2, and not just in the chemicals industry, but also in the energy industry, because when you pass through the supercritical point, you have a thermal transition that allows you to have heat exchange, which means that you can use supercritical CO2 to store and use energy. So imagine what the implications are for the solar industry and the wind industry if you can store the energy that is being generated when people don't need it and get it back using CO2 as a storage medium. So we're using a climate change gas in a closed cycle to be able to store and reuse energy from renewable sources. All right, so that's supercritical CO2. And it works in a closed cycle. So that means that it becomes a technical nutrient under cradle to cradle. It operates in a closed loop. And what that means is we can capture it and we can keep it without releasing it to the atmosphere. So, here are some examples. This is a CO2 dishwasher. It's true. It's on the market today. You can buy one, you can use it. What it does is, because CO2 is such an excellent solvent, it releases the supercritical CO2. This closes. It releases the supercritical CO2 in the compartment, washes all of the dirt away. The dirt is cleaned out in the filter, and the supercritical the CO2 is returned to the compartment and reused. What an elegant product. No water. No water. People look at that and they say, no, 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 that's not true. This can't be. It's impossible. All right, so from the energy point of view, this is not the diagram of the human reproductive system. These are not kidneys, right? These are combustion chambers. This is an actual working model of a turbine that is manufactured by Sandia Laboratories, and it's coming commercial this year. Now, why is it so important? Turbines are the #1 way that we generate electricity across Europe. Whether it's from nuclear or from gas or whatever, it all goes through a turbine to generate electricity. So turbines are basically what everything is running off of. When you replace gas with supercritical CO2 in a turbine, you reduce the physical footprint of the turbine by 90%. In other words, you're generating the same power for 10% of the footprint. Think about that just for a moment. It's an amazing development. Now, why is that? The reason for it is because supercritical CO2 is an excellent lubricant. So it just goes through that turbine like grease, like oil. It just goes straight through it. And also, it's quite heavy compared to gas. So it has a lot of inertia to it. So it makes the turbine run with a lot more force. That's what's going on right now in the marketplace. This is entering the market at the end of this year. So this means that we can start to use CO2 to greatly increase the efficiency with which we generate our energy. So when you start to put this whole story together, you begin to see a potential solution to our climate problem. And the solution is CO2. Yes?
What is the product, what comes out when you, yeah.
Well, it's like everything else. When you have the, it's not like a jet turbine. It's a closed cycle turbine. So what happens is the CO2 goes through the generator and comes back and gets reused again. So it's all done in a closed cycle. Oh, and sorry, by the way, just to show you how fast this is moving, in the United States in 2007, there was no investment in this technology. And last year, they were investing $500 million a year. So it's just going like this.
How do you how does the CO2 stay in this supercritical stage?
It doesn't have to.
Okay,
that's the advantage, because what happens is that when it, as you know, as gas goes through the turbine, it expands. Mm-hmm. So you lose your supercritical state, but it's not lost sufficiently to cause a problem, and then it gets recirculated and brought back into the supercritical state.
Yeah, but my question is about, you have CO2 in the air
Yes.
from pollution, and you have to bring it under a pressure from 72 bar.
That's correct.
Correct.
Yeah.
So there's for energy needed. And
Good, very good question. So the way that this is done, is being done profitably right now, is Mitsubishi Heavy Industries has developed a CO2 recovery technology for the chemicals industry, which allows them to recover the CO2 and sell it as a product at market prices. So, and I appreciate you asking this question because it's one of the most important questions. What we're doing right now with carbon capture and storage is we say, oh, no, you can't do that, it's too expensive. I mean, as you know, the experience in the Netherlands was they tried it a few years ago and tried to get Dutch taxpayers to pay somewhere more than €1 billion for CCS. And actually your former Prime Minister was brought out to try and sell everybody on this concept. But you know, the Dutch taxpayer, they really had sense and they said, no thank you, we're not going to pay for this. It's ridiculous, and they were right. But if you combine the capture with an industrial use of the chemical, you get an internal subsidy. And that's where your profitability happens. It's exactly the same thing as with the Herman Miller chair. If you integrate your processes, and that's what Cradle to Cradle is all about. It's about integrating holistic quality. That's where your profitability comes in. So you can subsidize the CCS capture with the sale and reuse of the product. And that's exactly what's being done today. So all of those examples that I just gave you are based on this part of the graph. The reason I want to show you this graph is because some of you I know, and a lot of the students have seen it before, but some people have the idea that all of this is cradle to cradle, and it's not. The reason that this is shown is because this is to show this is eco-efficiency, okay? And it includes recycling, which today is basically downcycling, and it includes reducing your negative impacts. This is to show that there are transition technologies that can bring you up to being less bad, that give you some leverage to get into being on the positive side. But to be clear, the cradle to cradle part is here. It's not here. So the reason I say that is because a lot of companies think, oh, we're reducing our negative footprint, so we're cradle to cradle. No, sorry. You have some nice transition technologies, but that's not cradle to cradle. The cradle to cradle part is up here. Redesigning with innovative new uses, reusing at a high level of quality, and upcycling the quality of your materials. So, I'm going to give you an example of this with supercritical CO2. So with supercritical CO2, you might be, for example, you might have a coal generating facility where you can use supercritical CO2 to store excess energy that is not used. And what that means is you may not have to build another coal generating facility. So that's what we call the transition technology. So the first thing is, let's at least try and slow down this massive construction that's going on right now of these coal burning facilities by using these types of technologies for energy storage. But the true cradle-to-cradle application of it is, if you have a windmill, as you do across the Netherlands here, that is generating a huge amount of electricity that is going into the air because no one's using it at certain times of the day and night, imagine what this will do to the efficiency of windmills. If you can use supercritical CO2 and these types of generators to store and generate energy, your cost effectiveness of your wind energy is going to go up considerably. That is cradle to cradle, because you're using efficiency of new technologies to improve the productivity and profitability of renewables. That's the difference between this part and this part. That's why I just wanted to clarify the distinction.